Our first talk for today is E.Lupercio, who is going to tell us about self-organized criticality and tropical geometry.
Thank you so much. Thank you so much for the invitation to speak here. It's a great honor. It's just a fun talk with lots of pictures of these things that my talk has two parts, a physical part and then a mathematical part, and I will talk about these two things half and half. The first one is well, we have been doing these things that are, I don't know, in mathematics we would say mostly conjectures, or in physics you would say observations, I don't know what you would say, but think of the first half as a physics talk and then the second part as a mathematics, or something like that. In other words, I'm going to first be speaking about self-organized criticality, and just as this is not a pipe, well, this is not mathematics. Most of what I'm going to say in this first half we did with big computers. We just did it with big computers. Yes, and additions and subtractions, no more than that. Additions and subtraction of natural numbers. We didn't even...
In maximum. Absolute values, yeah?
Well, yes, then we did that, yeah. But in the first part, not even multiplications. And then, of course, we used the tropical algebra in the second part. So we use this supercomputer, and we use this other supercomputer, that is a little bit more spectacularly decorated, called Xiuhcoatl. This is the fire serpent, and the most beautiful Xiuhcoatl sculpture in the world is not far from here at the British Museum. It's very beautiful. So this is the fire serpent that guides Huitzilopochtli through the darkness. So let's try to use it to guide us through the darkness. And so well, let's start by describing the sand bicellular automaton that is the starting point of this story. So the sand bicellular automaton it's just this, you think of a very large table and made of very small tiles, tiny square tiles, and you record at every tile the number of grains of sand that are located at that tile. So in this example here, we have 2 grains of sand, no grains of sand, and zeros. I'm going to simply not write anything from now on. It's the only zero I'm going to write. So
only even numbers?
No. This is a 1. Any number, any natural number, any number of grains of sand. And it's just a zero automaton. And in this universe, there is only one law for this. In the physics of this universe, there is only one law, and the law says that the law of the only law. Well, there is discrete time, and then there is only one law of evolution in this universe. If you have no grains of sand, nothing happens at this location. If you have 1, nothing happens. If you have 2, nothing happens. If you have 3, nothing happens. You are to think that the tiles are more or less of the size of the sand. But then, when there are 4 grains of sand or more, in a unit of time, spontaneously, they go to the 4 neighbors. So this tile ij, the value of this tile ij goes to ij minus 4, and the other ones j go to ij plus 1, etc. So they just spontaneously go to the 4 neighbors.
Even in next, I think it will be much larger value. It still goes.
Even if this is much larger, because the original model you thought they were little springs with torsion, but anyway, this is just a way of thinking. It's just a cellular automaton. So if this is number is very, even if the other number is larger, it goes to the 4 neighbors. So this is some state, and then well, there is an ambiguity in this rule, in that this action is called topple, this ij. We topple that tile. And there's an ambiguity in this story in that we could topple that one, or we could either topple this one or topple this one. Which one to topple? And there's a remarkable property of this cellular automaton.
So you take only one, yeah?
You take only one.
And not everywhere, yeah?
No, you take one and topple it.
Yeah, okay.
One and topple it. One and topple it in a unit of time.
It's the largest value, yeah.
Huh?
Takes the
No,
largest.
you take any.
No, just any.
Any, okay.
So there is an ambiguity. There is some randomness in this, in that I'm not saying which one to topple. But there is a remarkable, although totally elementary theorem, but remarkable nevertheless, that says that it doesn't matter. For the final state is unique. Once you get to the theorem says you reach a final state, this process is finite, you get there, and once you get there, the final state is totally determined by the initial state. And there were many ways to get there. There's some randomness in the choices of ways to get there, but once you get there, it's a unique final state. That's a nice exercise. You can try it.
It's actually analogous to diamond lemma and Grobner basis. It's completely the same.
Maybe it is for some reason.
Yeah. And there is an equivalence that I will mention later on. There is an equivalence with some sort of functional analysis, but let me just continue. So, but now physicists, the physicist proposed this model, Perbach, Wiesenfeld, other collaborators. They were studying what they call now complex systems, things that are very complicated, that have a lot of nonlinear interactions, and that kind of the archetypical example for them is the seismic earthquake systems of planet Earth. Somehow they display statistics, as I will mention later in another these pictures. They display statistics very similar to the statistics that are displayed on systems that are on phase transition. When water is becoming ice, I don't know if you have seen the videos on YouTube or anything like that, we see these lines of ice forming, and then this kind of line on the lines of ice, and then lines of ice, and it's very fractal when it's freezing. The moment that it's freezing, in the phase transition, you have these power law statistics that you can see literally on the videos, or you can compute with statistical mechanics. And they realized that there were all these physical systems that displayed the same kind of statistics. But the mystery is, well, in the phase transition, you have to tune very carefully and very intently the temperature, the pressure, and all this. The physics call this fine-tuning. And for fine-tuning, it was reasonable you would have this kind of situation. But it was surprising at the time that you would have this kind of the same thing as in phase transition, same mathematics going on all over the place, same equations all over the place. But you didn't have to do fine-tuning. The system, the dynamical system alone, somehow they were saying, tuning itself, self-organizing into this critical state. So that's why they call it self-organized criticality. And then they provided this remarkable example that it still has many mathematical mysteries. Most of them, almost everything they said is a conjecture even today. But some things they said has been proved in the last couple of years, in a resurgence in interest of the subject by mathematicians. And they said, well, why don't we take a lot of sand at the center of the table? And the table is very large. Why do we take a lot of sand at the center of the table? And for example, in this computer experiment, we take 1,000 million, English billion, not a French billion, 1,000 million grains of sand at the center of the table. And then it's amazing what happens. You get this very structured picture that
So 0, 1, 2, 3, yeah. Yes.
0, 1, 2, 3, 0, 1, 2, 3. and you get this extremely elaborate picture. You see even more colors because the dots are so small that your eyes interpolate the colors. But it's really 0, 1, 2, 3, just those colors. And this takes an enormous amount of time on a supercomputer. And you really need to do a lot of additions and subtractions. But it's very mysterious. How can I explain with this phenomenon? How can we mathematize this structure? Already physicists said interesting things. They said in the original paper that this was a self-organized critical state, just like the earthquakes. And what they meant by that, and this is the original paper, this is the 1987 paper, where they propose this example. The remarkable paper is very short, 2 or 3 pages, and it's the most cited paper in all of physics in the decade of the 1990s. 2 or 3 pages, but it ignited the imagination of to model a lot of phenomena in nature. They propose the term self-organized criticality. 1 over F noise is pink noise, and well, one sees what they could do in 1987 is kind of funny these days, because they could do 20 by 20 and 50 by 50, and not really much more than that. Nevertheless, what are they doing here? What they are doing is, once you reach this state, then they throw 1 extra grain of sand at random anywhere, and they measure, and they let it settle, and they measure the size of the avalanche. So this produces some avalanche, and it stabilizes, and it has a size, and they measure the size of the avalanche, and they do this many times, and they do the statistics. They do the histogram of the size of the avalanche over a number of avalanches. But of course, they take the log, and then they get this straight line. And this is evidence for them. And of course, here starts the discretization starts to do things. And of course, for them, this is an evidence that this has this fractal structure. They couldn't do this picture by 1987 at all. They couldn't do this picture at all. But this is what they do in the paper, and for them, this is the evidence that this is one of these self-organized critical states, because it behaves precisely like the frequency of earthquakes on planet. This is all of planet Earth, and then you have how many earthquakes of what magnitude. Same story, and log, and this is a well-known thing. I forgot the name, but it's a law in seismology that. And different regions of Earth have different graphs. This is planetary-wide, but you could do Santiago de Chile region, Mexico City, and Istanbul, and they have studied this very carefully. And the exponents vary a little bit depending on the region. And of course, here with they found the same behavior. So these earthquakes are behaving just like these earthquakes, and then we can model. And it was very used successfully because when they were trying to study earthquakes, the best they could do was to write these very complicated partial differential equations. And first, it was even more hopeless at the time to actually compute with these partial differential equations on the computer. And then it's really hard to model. They keep putting more and more. You can see the books, and they keep putting more and more terms, and it's really hard. It's a really hard. To go from Newton's laws to the behavior, the global behavior of earthquakes on planet Earth, it's really an open problem, really challenging. And different models give you parts of this behavior, but the SandPile model, that is just a cellular automaton, gives you a lot of the properties of the behavior, and it's a very simple model. So this was very successful, of course, especially at the time in which computing was so expensive and difficult. So that's the story, and this was very successful. Then Perback, this is a paper that just appeared on Quantum magazine last week or something like that. It's a popularization paper. Nevertheless, Perback went on trying to say, well, maybe this can model this and this and this and that. before dying. And one of the things that he said is the self-organized critical hypothesis for the brain that he proposed, that said, well, the brain must be on a self-organized critical state, and this is very looks like very fine-tuned to process information, but looks like very fine-tuned to process information, but it's a self-organized critical state. It self-tunes, and this at the time looked absolutely hopeless to even try to verify. But now they have these things that they use in the CERN, these things to measure very fine things. You know, now they measure when one neuron turns on another neuron and another neuron, and how many neurons and what's and they measure these avalanches. Now they can measure these things, and now there is a very deep discussion in neurosciences whether it's subcritical or nearly critical, and they have and mathematically these are slightly different kind of situations, but still Perbach's hypothesis survives the era in which now they can do these extremely fine measurements in the brain. So it's useful for model. Let's just say that this self-organized critical concept that is not very well defined, there's not a mathematical definition of the concept, it's useful for modeling things, you know. You just say, well, a self-organized critical system has these 20 properties in general, and if you get them, then you are in a self-organized critical system. There is not a mathematical definition for this. And then, but it's very interesting. But if we zoom in that picture, if we take this picture and we zoom in to the picture, then we, of course, start to witness these tropical curves. I don't know if you can see them, they are very thin, but they appear there all over the place. In these regions that are dark, then you see all these regions that have 3, 3, 3, 3, 3, 3, 3, they are 3, 3, 3, 3, 3, 3, 3, then you see these tropical curves inside the regions. So it was, Grisha Michalki immediately noticed that these are tropical curves, and this kind of started all these investigations. Okay, so again, if we take, we do some rescaling a la renormalization group. We do rescalings by the square root of n, where n is the number of grains that we are dropping at the center of the table. So when we do this, so that they look of the same size, and it is an open mathematical question that this mathematical object exists. Pagin and Smart proved that it exists in the weak star topology. That kind of destroys the fractal structure. That there is a limit in the weak star topology, but nobody, as far as we know, has been able to prove that this mathematical object exists. But it seems to exist in the computer, and when you do this zooming in, then you see these families of tropical curves that are very interesting. Even the sequence of tropical curves is very interesting. And one could say a lot of experimental things. I will say just a few experimental things that one can look from this. So Kalin and Shkolnikov provided the first proof in the field, proving something, and this is a theorem, this is mathematics, and they prove the following theorem. And is that indeed, if you take this, you take this convex region and you take some mesh, some size, and you do the sand pile, and you put 3, 3, 3, 3, 3 here, and then you drop 1 grain of sand, one at a few locations, a few finite number of locations. Then you drop here, maybe it's a 4, and maybe here is a 4, and maybe here is a 4, if you take these locations and you put these these additional grains of sand, then and you do it rescaling by the you do the rescaling as epsilon tends to 0, the limit C is a tropical. So they prove this one. I'll try to explain the proof of this theorem.
The tropical curve consists of 2 or what is it? You get diagram of 3 and 2 or something like this.
No, well, the points, the set, the C epsilon is the set where the squares not 3. The square is not 3. So it's a set. It's a set. And in the Hausdorff topology, this.
So it depends on the shape of the convex region and collection of points. You get something.
Yeah, on the shape of the convex region and the collection of points, and then you get a tropical curve. That just depends on the collection of points and this
It's
also
minimize something.
minimizes symplectic area. Tropical symplectic area. And this minimizes some sort of Steiner curve. Steiner. Some sort of Steiner curve. So I can explain in 1 minute the proof of this statement if you want, or I can go on a little bit. But let's see it in action here. If I drop, this is the table, and I'm going to drop a grain of sand, and then the avalanche is occurring. This computer is 2011, but so the avalanche is occurring there, and again, white is 3. White is 3, and there is colors for non-3. And then you see the avalanche occurring, and you see that as the avalanche stabilizes, you get a tropical curve.
Which contains the original points. Yes.
Which contains the original. So it solves the problem of finding this Steiner curve passing through the points. Steiner curve passing through the points. Passing through the curves.
But the tropical curve is arbitrary irrational direct slopes, yeah?
They're rational slopes.
It could be all rational slopes, yeah?
Could be any rational slope.
So you get something like integer piecewise linear functions and try to minimize something.
That's
Values
the
at this
proof,
point, yeah.
The proof is, I can't explain the proof. It's very simple. But it's what Maxime just said.
Just try to guess, yeah.
I'll just say the proof. It's exactly Maxime said it in 1 second, but I can say it in 2 seconds. So the point is to consider, I will just say it in 2 seconds, the family of piecewise linear functions, C slopes, well Q slopes, I don't know how to call it.
Maybe this slope.
C slopes to f equal to 0, f bigger than or equal to 0, 3 concave, and 4 not smooth at pi, this family, and then the points, the blue points. Fp is mean Fp, and the theorem is that the final state of the sand pile is the initial state plus the Laplacian of Fp. This is the theorem. So it's a minimization situation.
Okay.
It's a minimization situation. Okay. Well, that's very nice, and so far so good. So that's the thing. here we have the same situation.
Minimum, I mean, pointwise minimum of such functions.
Pointwise.
Which is also satisfies the same constraint.
It also satisfies the same constraints.
Yeah, it's kind of minimal point of this context.
Well, this is the same. I just did it.
So I think it should be related to other stuff. Mathematics. It's by Donaldson Tian about fun of varieties. And there is a story about extreme metrics, and in Toric case it's something pretty similar which should go. Maybe not exactly.
Ludmil tried to warn me about this fact. But I haven't processed it yet.
It's maybe slightly different story, but
Ludmil mentioned this relation to Donaldson Tian, but I haven't processed what he said yet. So I'll try.
It's maybe some kind of tropical Calabi conjecture.
Yeah, it feels like that, definitely. I'll say more about that later. Anyway, this is a fascinating example though, because this is non-commutative geometry. Samples don't know they are on their sand polytopes. They just know they are on convex sets. And that's where quantum toric geometry will come into the picture. Samples, they just don't know they are on their sand, they don't care to be on their sand polytopes. They only care that your set is convex, and in fact, they only care that your set is convex and not the following convex set. Every other convex set under the universe is right, except the following convex set. This convex set is a no-no, irrational. For every other convex set in the world, the sample
What is the version of it?
just a parallel two lines of irrational.
Yeah, it's bad. Yeah.
That's the only bad set. The only bad set in the world. Every other convex set in the world, it's kosher. So this is a beautiful example, extremely beautiful example. In fact, from this, Nikita and Misha wrote the following formula, which is very beautiful. Let me just write it.
It's also halal and haram, yeah, because as a religion.
I'm ecumenic, you know, I'm totally.
The convex set is the table?
Convex set is the table.
Why does it have to be convex?
Well, no, the sample doesn't care, but the things
Theorem,
that we did, when we are proving things, sample knows too much about resolution of singularities, in fact. But let me just say
What
that
does it mean the table? So it means they drop when they go to the boundary to outside, yeah.
they just fall.
They fall, yeah, okay, yeah. So
Just fall into the infinite voids.
yeah, okay, yeah.
And let me just say very quickly that from this picture you throw just one grain of sand at the center of the table, and then you compute the tropical curve in the limit. Then it gives you approximations to the circle, of course. And it is it in particular gives you this formula. Which is very nice. Just a formula, but it's very nice.
Good.
Just a formula, but it's very nice.
What is F?
F is the length of this vector plus the length of this vector. Just from the picture, you can minus the length of this vector. From the picture, you can obtain the formula from this. Well, 1/4. That's why I put 1/4. Huh? That's why I put 1/4. But yeah. So this is Kalinin Shkolnikov. It's in the archive, the proof.
So it calculates the area of the things.
Yeah.
What is the meaning of this? Means f is some real number, and this is a
You take
matrix.
ABCD.
ABCD.
ABCD, it's a security matrix.
It's a matrix, and the answer is a real number. 2 minus
Yes. Sum of all matrices.
All matrices. It's a function on matrices.
The function of 4 variables.
It gives you a number. It's a function from SL to Z to reals. Function from SL to Z to the real numbers. And yes, Maxim already has a proof,
So
but you
f
can
is
do
a
it.
function.
F
It's
is
this
a
function. It's the given
And
function.
sum of infinitely many numbers is equal to one number, which is minus one.
Okay,
What,
okay.
what
Sorry.
is
No,
this?
Series are confusing, I know.
Which symbol is this formula?
Series are confusing. But anyway, so this is a remarkable example, and it has
So
to
f
do.
is some compact support.
Well, no, no.
It is
F,
written.
F of A, B,
There
C,
is
D
a
is
formula
written.
for
Okay, f off, but there should be another bracket then.
Oh yeah, okay.
So I,
Very reasonable. If you see A, B, C, D twice on the board, yeah.
no, I mean there is another bracket with the, so f of some matrix gives a real number. That,
Yeah, oh, you could put entries of the
There is
function.
another bracket there.
Oh.
What was the problem?
You want parentheses around the
Here
matrix.
maybe.
That's on, yeah.
Oh, another
The number of
bracket.
parentheses should
Oh,
match
okay,
number of parentheses. Yeah, okay.
Now we are okay.
Now I understand.
Okay.
Anyway, let's not lose more time. There's lots of ground to cover. But anyway, this is non-commutative geometry. It's the toric, quantum toric geometry, and that's where it connects to our work with Ludmil and Laurent, Maxim, and Arrangé.
So why it's so nice formula? Because it's not a simply invariant picture.
Yeah, it's interesting. So exercise, look at it.
No, but you take SL to Z plus.
Plus.
No, because
Plus.
I think for the whole SL to Z, this is some is standard. If you take the whole matrices and
It's simple to C plus. They have to be A, B, C, D
Yeah,
positive. A, B, C, D
no,
positive. A, B, C, D positive. Yeah, right. Positive. That's right. That's right.
Yeah, in fact, I've seen many formulas like this.
Yeah.
Yeah, it's.
But the
like
bad
Max-
is that just
like
the,
Max
just,
Chain
just the
identity.
simplest sample in the universe gives you
Yeah.
that. Just the simplest sample of the universe. You can get in the convex set and start getting formulas and many the moments of this. This is just etc. Yeah. Anyway, this is the timeline for
sorry,
self-organized.
Ernesto, sorry, I thought it takes the square.
The square. Square. Yeah. So
No, not there. I get it.
the square.
Okay.
The square.
Square root, yes.
No, but разность. Есть треугольник и в квадрате.
The square. You are right. Absolutely. I'm sorry. I'm messing up. Well, you compute it carefully and you get this. And it's what Maxim said. You just compute this area. You get this thing. Okay. So, but this is an interesting timeline because, so Bach, Tang, and Wiesenfeld 87. In 89, Kalanov proves this fact that, from the physicist point of view, scaling and universality. Dar, in 1990, discovers this group structure on samples in the recurrent states.
It's a first homology.
That's right. But of a tremendous graph, if it is a big sample. Exactly, but it's not just that group of divisors or whatever. And then Mana calculates the exponents in 1991. Finally, they calculate the exponents. Caracciolo, Pauletti, and Sportiello in 2010 noticed the piecewise linear patterns. They noticed the piecewise linear patterns and some dynamics. They are extremely clever. Now Kalina and Shkolnikov in 16 prove this theorem, that theorem. The idea is this minimization, but then you have to be very careful and it has a lot of things to check. And Bupatirac, Johansson, and Harald finally give formal proof of this power law from 1997 in 2016. And they use all these trees and the structure of the all this. It's a complicated combinatorial paper. There may be another proof as we will suggest. Anyway, the wave operator, let me explain the wave operator. This thing that you saw all the avalanche occurring. But from soliton theory, physicists suggested, and then one can define this wave operator. I'm going to apply just the wave operator here. This is just, and then if I apply it again, and again, I'm dividing the avalanche into controllable pieces. I'm dividing the avalanche into controllable pieces. So this is the avalanche, but I'm dividing it into these pieces. I will write the formula for this operator in a second. And then,
Yeah, but it's really exactly these questions which I discussed in my third lecture, hidden form, yeah, that's moving families of
Yes.
curves, yeah.
that's right, that's right,
That's
exactly.
literally the same, yeah.
Exactly. So, but I will write the formula, and that and and we really have to understand Maxime's third lecture because this is something that we wanted to know, of course. Anyway, the formula is this is the delta function of P. This is toppling. And this is relax, the whole thing. So this is the formula for the wave operator that this is the one step of this. And if you understand this wave operator, then you understand the proof that it passes through the points and all that. It's another way of thinking about it. So you put one more point there, you just topple there, then you take one from there, and then you relax.
Yeah.
That's the formula for the wave operator.
Take some of this
And
function.
that's what I'm doing here. And this, you can prove then that applying this wave operator iteratively, if you apply this wave operator iteratively, you do the avalanche. That's what you can prove.
Okay.
If you apply iteratively this wave operator, and of course this gives you a flow, and this is this is a flow on modular space
Of tropical curve.
of tropical curves. This is a flow on modular space of tropical curves, and of course for tropical
What do
curves,
you mean by modular space of tropical?
It's piecewise linear convex function.
this is what linear convex function.
How this is a modular space means? So
There
what is
are real parameters here.
It's a real. Everything is real now. No, it's a continuous thing. No, it's a continuous thing, and here you have, well, the wave operator. I mean, this was just a picture, but it's what I just did. It's what I just did. So with the wave operator, you apply it and apply it and apply it and apply it, and then you get to the curve. If you apply it and apply it and apply it iteratively. So you divide the whole avalanche into these operators that can be written in terms of tropical geometry, just because you just add 1 to the coefficient of the, you just add P. If the coefficient of that plane, Aij plus Ix plus Jy, so what you're doing is you are adding 1 here.
Ah, so the domain's labeled by pairs of integers. Yeah,
Yeah, yeah.
that's a derivative.
Yeah, yeah.
Okay.
So like this, and then you just add 1 here. And this produces, you are decomposing the whole avalanche, well, T, from T0 to...
But if you do this in Legendre transform, consider just convex functions on domain in this square area. Like this here.
But you are dividing the process into these paths.
Yeah, no, but why don't you formulate the whole things in Legendre transform in terms of you get just convex function, sum over, you get some Laurent polynomial maybe on non-Euclidean fields, you get norms of coefficients, you get some convex functions. It will be not so pictorial, okay, but it's
Okay, we'll try to process that. Perfect. That sounds fantastic.
yeah, it's good. Let's try to do this hard calculations that will do simple calculation with smaller numbers.
Okay, so here is the but now we use this to our benefit to do the following thing. Now we say, well, all these models that the people really use to study self-organized criticality, all of them really are discrete cellular automata. But now this is not a discrete cellular automaton anymore. This is paths on this space of functions or whatever, this space of curves. Now this is a path on the space of curves. This is a continuous thing. So we just have to understand what is the size of an avalanche. And what we do is we do the following. We say, well, the size of an avalanche, let me do it here. The size of an avalanche is how much this symplectic area changed. So we have some points, and we have this curve. For example,
Symplectic area of what?
of the tropical curve.
You mean
So let me explain the situation. Let me put it here. Here. Now you have many points, and you have a tremendously complicated tropical curve of a very high genus. Enormous high genus. This is the cellular automaton. This is the tropical geometry. And it doesn't project very well, but it looks exactly the same. So this is tropical geometry. Now we have this tremendous high genus curve. By the way, conjecture, someone may be able to prove this fun fact, that it's experimentally, you can observe it. Nikita,
So what do you mean by genus, high genus in case of...
for tropical curve, that's a genus.
the number of cycles of the graph,
It's like small tubes.
number of cycles of the graph.
In case of tropical, that's...
First Betty number of graph, yeah.
The first Betty number of the graph, this enormous genus. Now, well, let me not say the conjecture because it's a fun fact. It's just the fact that if you take up the points, Nikita claimed that one could prove this easily, but now well, we haven't tried very hard. But it's kind of fun that what you obtain is a connected tree. If you subtract the points, for generic points, you subtract the points, the blue points, then you get a connected tree. And this is fun, but we have
Blue points which where you originally put your
yeah. If you take off the points in this picture,
which points?
the blue points,
On which you already put things.
you get a connected tree. It's funny.
You get genus 0, yeah.
Yeah, and we don't know why. Yeah. Anyway, now you have this. You have a normally high genus, and now our mathematical model for earthquakes is the following: take this enormously high genus curve, and now we claim that a very high genus Steiner curve is a self-organized critical system. That's our claim. We claim that a very high genus. So this is the story. Well, I erased the story, but the claim is a claim, conjecture, or whatever. A very high genus C, drop, or maybe not drop, if you understand better, is a self-organized critical system. And what this means is the following. What this means is that if we put one more point, we throw one little more point, and then we apply the wave operator increasingly until it passes through that point. So there is a path on modular space until it passes through that point. The size of the path on modular space, the statistics of the size of the path, is the size of the path on modular space is like this. Maybe now Maxine can prove this, but what we did is we put it on the computer.
Size means length.
Yeah.
What is size?
Well, how much the symplectic area changed, for example. How much the symplectic area changed. There may be a better measure of the size, but for nearly any reasonable measure of the size of the path, you will be in self-organized criticality. Not only that, many other things of self-organized criticality will occur for this self-organized critical system. This is just the first check, but we believe it is a self-organized critical system. All these other things will also occur. I'm just mentioning one. And, well, here it is. We put it on the supercomputer. It takes a long time. And it's true. So we put it. We just measure the thing, and here we get. This is the classical samples, and this is a very high genus tropical curve. It's a very high genus tropical curve, but not one. It's millions of them. You need to check. We did it for many of them. And so indeed, it behaves like a cell. When it gets to very high genus, it's an emergent property. For low genus curves, you don't see this. But once they are of enormous genus, it's a self-organized critical system. Now you would say, well, this is funny. But you can actually use it to model, because now it's a continuous model, and it's linear equations, and now it's really fast. Now it's a much, we also claim it's a much better model. It's just a great model of self-organized criticality, that can replace these sand piles in all these modeling problems and the brain and whatnot. This model for self-organized criticality is so much more amenable to computation that it's much better model. That's our claim, that this is a much better modeling tool for self-organized criticality. Intriguingly, we also claim, because I mean, in the examples that we have been modeling, so to speak, we're interested in biology or whatever, and then there is this mystery that people study very heavily and in a way, Vera Kalinina, the biologist in our team, observed that this may be used for modeling of something called proportional growth in biology. Dar also went into that direction. And as a warm-up problem, they already have in the surveys of proportional growth in biology, they have, if you read the surveys, there is always one paragraph for, and then there is this model that is piecewise linear that try to explain. The mystery is why, when an animal grows, or a plant or whatever, it knows how to, what proportion as you grow, to grow your heart and your liver and your head, so that you grow proportionally. How does it manage, with what local rules it manage to do this, have this proportional growth? And it's a hard problem. They already have, if you see the surveys, there are many competing models, and one of them says piecewise linear. And of course, when we say, well, what if? But this is a much easier warm-up problem. This is for semiconductor building. This is an actual.
It's kind of crystal growth. Yeah, it's a space.
Yeah,
it's actually it's very. The fact that you get this kind of rational slopes was known for 50 years.
But we would like to modify this into the biological modeling. Hopefully, we think it can be done. We haven't worked so much on this, but yes, this is the tropical curves that appear already in the crystal growth, but it suggests that these models could be more flexible to be applied into the biological model. Okay, let me just say in the last 10 minutes, because really now the second part of the talk, now I turn this off. Very well. And this also is related, of course, to our work. Well, I'll just mention it, two things now, because I'm really running out of time. But we have this quantum toric geometry.
It's three-dimensional partitions, 3D partitions. Yeah. No, this story which is already discussed for 10 years in string theory. Because in the 3D partitions with some symptotic, you then get quantum curve and mirror colliders revolve or very large. Yeah.
It's probably that. I don't know. I don't know the story, but it's so. I should check that. I should ask you a few questions after that. But well, what we have is quantum toric manifold.
I mean, quantum in plain sense.
Is X is an equivariant compactification of a quantum torus. This is, I don't know what letter it is. This is an equivariant compactification of a quantum torus.
It's kind of algebraic, yeah. Q is not absolute value 1.
No. Q, well, this will be in one-to-one correspondence. The category of quantum toric manifolds with quantum toric maps will be in a one-to-one correspondence with quantum facts. So I can tell you what is a quantum fact.
Equivariant with respect to what? What is equivariant?
Well, the action of the quantum torus.
Quantum torus?
Yeah, but he said this is a compactification.
Equivariant compactification.
Equivariant means what?
This is actually torus action. Usual
torus
torus action.
Usual torus.
The torus. For me, of course, most people here think of the quantum torus as an algebra, but I will be thinking of this as a very, I don't know, non-separated stack. So they end up being Kähler. But with fans, it's of course not Kähler. If I put polytopes, then it's Kähler. But with fans,
Yeah, in fact, I think the talk of Diniarou was secretly about this.
huh?
Talk of Diniarou was about.
Yeah, of course, yeah. It's what we know. Of course, we also know this. That it's why this is example. Yeah. Well, there is that. I can tell you what is a quantum fan. 100 out of 10. More or less. A quantum fan is just a fan simplicial fan if you want, together with a deformation. Together with a deformation parameter. So we have this so this is a quantum fan.
So you get lattice. So you get maybe two different as integer structure and fan is integer for one structure and lattice is.
Well, these rays have to touch gamma. I didn't say that, but these rays have to touch gamma, and we have to choose a Planck length on any ray. We have to choose a point on every ray. On every ray. That is like choosing a Planck's constant on every ray. Planck length on every ray. And so we have this quantum fan, and from the quantum fan we can produce from just this we of course have a quantum torus. Just from phi. And from the fan, we compactify the quantum torus. So if I take x from RD, I don't know, comma gamma, I get into S1D containing something. I don't know. And this is the holonomy of the quantum torus. Torus as a Kronecker foliation. And so this gives me the quantum torus.
So Kronecker foliation is some irrational slope. No? So what is that? I didn't understand.
I'm going too fast. I'll tell you a little bit, but it's just I can explain this much better, of course, but I'm going just too fast. So this is this transversal is this, and this dust here is this. Is that? So we have this quantum torus, and we compactify the quantum torus using the datum of the fan, and we get the quantum torus variety.
So then it's unitary, yeah, because you do real kind of junction.
Huh?
Then the Q has absolutely one, yeah.
Q, yeah, has absolute one. Absolute value.
Star.
It's star. It's absolute value. It's the usual quantum torus, just the most classical one. Okay, so we compactify this quantum torus, we get these Kähler stacks, Kähler toric, and as Maxim said, example, for P1, Well, we get the classical P1, of course, we could get that one if h bar is 0. But if h bar is not 0, then we get a quantum P1. And then this quantum P1, so this is the Hopf, and this is what was mentioned in Denis' talk. And now we get and this is all this parameterized by this h bar, but really by the Gale transform of h bar, let me call it lambda, by the Gale transform of h bar, that is lambda, and well, I won't say much more. But lambda is a coordinate for the modular space of P1s. And this can be done, this modular space can be done not only for P1, that has, the orbital point is classical P1, we have the rational points that are the so-called footballs, these weighted projective P1s, and then the non-commutative P1s. There's an absolutely analogous picture for any toric variety. We have this modular space, and the samples tell us how to go about resolving the non-commutativity. But I will not mention that story, it's already too late. But, yeah.
Thank you. Any questions?
Sorry, what the quantum, like, was the quantum verge geometry independent of the story about
not entirely, but I can tell you more or less. We use the sandpile story in the quantum theory geometry to understand these objects. The sandpiles guide you on how to understand these things. They seem to know a lot of things about all these objects. Of course, not the sandpiles, it's the convex function. But
This function convex at integer points that appears in different subjects like Ilfan-Zetlin basis or Born conjecture. Yes, it's by run
very
transforming
universal
do something.
Any more questions? Let's thank Ernesto again. So we'll resume in half an hour.